Thanks for the invitation to speak here today. Uh, interesting workshop. I had a hard time figuring out what to talk about. My name's Jan. I work on haptic science, devices, robotics of different descriptions. Before I learned about kind of the core of what we do is haptics these days. Before I knew what haptics was, actually was working as an artist in the early 2000s with a group based in Belgium. We got a commission based on this crazy idea of producing two walls within a museum as a commission for the Fano Science Center in Wolfsburg, Germany, a really big Zaha Hadid designed building. The idea is you create an impression on one wall by pressing into it, and that is reproduced magically at a second wall some 20 meters away. Permanent installation for the museum. Didn't quite know what we were getting into. My background's not even engineering. I'm a physicist by training, but figured out a way to do this. Upper middle, you can see a low frame rate version of the first prototype I made. So basically it integrates 4 sensors on the face, and I worked with a company out of Plymouth, UK, called Merlin Robotics on the design of this modified McKibben actuator that uses a shape memory alloy proportional valve at one end. And then we wanted to have many of these sort of tactile pixels in each of these devices. Cost was a serious issue. Our total budget, $90,000. Totally insane. So we engineered a leak at the far end. This is the early 2000s, but we figured out an open hardware microprocessor platform we could use. So these are all networked via Ethernet. The two walls communicate to each other. And there's a bunch of mechanics that goes into this. A lot of the initial designs were not acceptable because of all the requirements on building materials in Germany. But worked for a few days before the McKibben muscle started to fail. So actually, a huge issue in soft robotics is failure. So chemical stability over time, mechanical stability under repeated actuation, things like that. There are some noteworthy examples of engineered systems made from elastomers that can last a very long time. An example are pneumatic tires on vehicles, but overarching issue. Anyway, later I learned about haptics, which here's a definition you should use. Haptics is physical interaction with the world, physical sensory motor interaction. I won't say more about that now, otherwise I'll be talking about that all day. Our bodies have this incredible apparatus that facilitates this, both sensory, motor, and lots of other physiological systems that allow us to do all the amazing things that we can do physically by interacting with the world. Cognition on its own, outside of sort of interaction with the world, doesn't really make sense. This is a evolutionary phylogenetic tree for Animalia, the kingdom of animals. And we're down here in the lower right somewhere. Chordata is vertebrates, so we're down in some sub area of that. Primates, and then eventually Homo sapiens. Pop quiz. You didn't know there was going to be a quiz. Pop quiz for you. Which of, oh, is it, why isn't it updating? Where is it? Waiting for it to update. It's okay. I can do it without the pop quiz part. If it stops working, I'll just improvise. Which of these groups have possessed nervous systems? Any ideas? Someone help me out? Oh, sorry. Did someone give me an answer? Not quite all. So sponges, I think someone said this, I couldn't see sponges don't have differentiated tissues. These other animals, they all have to coordinate behavior across large bodies. It turns out that standard cell signaling processes, typically based on diffusion, are much too slow for this to be possible. I was sitting through half of the course on bioengineering. I wasn't teaching last quarter and realized it was totally impossible that these mechanisms being described could coordinate physiological processes and sensory motor activity across the body. And so animals really have this really distinctive specialization, which is the neuron that allows, rapid signaling across the body. We have many neurons, sensory neurons in the human hand on the order of 10 to the fourth, traveling along independent afferent fibers up toward the brain. So massively parallel communication network in them. One of the simpler, least or uppermost examples of animals on the tree I just showed that does have nervous system are jellies, here cnidarians, and even in these examples of animals with somehow the least developed nervous systems, what one sees is really remarkable repertoire of physical behavior. There's feeding behavior, hunting, planting. It turns out they sort of turn themselves into plants at a certain stage, anchor themselves in the sea basin and begin to digest their own brain, because you don't need nervous system so much if you're more like a plant. Lots of, I think nature, as people got excited about this field of soft robotics, it was sort of natural to see examples of soft robots like the one I'm about to talk about, and to think in relation to nature. Biological soft robots, so animals, much more complicated than anything than we've engineered, but I think of it as sort of a evocative grounding of these ideas that are being explored in soft robotics. This is a soft gripper that we investigated. This is work we published a few years ago. It uses a single pneumatic port to perform multiple gripping behaviors. It's formed from the casting of elastomers. So it's sort of a multi-part casting. Amazingly, it actually went quite well. So relatively few design iterations. We also introduced a high friction surface within the interior. What sometimes would be referred to as a gecko-like skin doesn't actually reproduce a lot of the specializations that allow geckos to do things like walk on a ceiling or wall, but has this microstructured pattern on its surface that facilitates load distribution across the surface and enhances friction. So basically this gripper works by a very simple device, but it works by enveloping objects, and you can compare it to fingered grippers, so soft or otherwise, that need to perform some sort of grasp and force closure in order to move things around in prehensile grasping. In contrast, here we just sort of wrap around it and envelop it and secure it very well using by inflating, surrounding it, and then deflating. I'll show a video in a moment. Oh yeah, here we go. It's a little bit slow frame rate, so you'll have to mentally interpolate. It's coming through Zoom, but can grasp onto a wide variety of objects. Because of the fact that we have this inflating cavity, we can reduce the pressure inside the non-closed cavity. So within that aperture, to perform vacuum suction by the same device. Can do interior grasping, exterior grasping, and multiple strategies. It's really just, I realized I should have brought the prototype with me. It's really just the control input is really just one syringe, either pushing air into it or pulling air out of it. One simple example. There are many other examples that find clever ways to exploit mechanics and physics in order to solve problems with minimal computation. And I think within this space of sort of grasping, the idea that you could do a lot of things with robotic morphologies that are not necessarily anthropomorphic or similar to the human hand is quite attractive. There are lots of examples of that. We published a perspective piece a few years ago detailing some of these. It can alleviate some of the challenges in doing sensing, grasp planning. So in addition to placing fingers, you have a robotic perception problem to figure out where to place them to interpret scenes and things like that. And these soft devices can often be quite robust, to less demanding on sensing and computation in that regard. I think one of the so within this broad space of soft robotics, there's been a lot of sort of creative work. I love the creativity and things like that. Functionality has lagged a little bit. Also, I get very enthusiastic about these things, but figuring out what they could be used for is sometimes a hammer and nail problem. But there are areas in which soft materials are widely used. One example is in textiles and in clothing. And so in this project, around the same period, we created these textiles. These are ordinary textiles that we transform into soft robotic muscles that can, so they scale to small sizes or bigger sizes. We can lift rather large things. Actually, now we understand the scaling a little bit better. We could tow an airplane with these things. I think it's nothing too surprising about that. I'll explain how they work. So conceptually, you could think of these as being roughly analogous to planiform musculatures or sheet muscles that you find in the abdomen and torso of the body. They comprise simple fabric sheets, so typically inextensible textiles combined. So there's two of those layers, and then within those, we introduce elastic tubing that fits in these stitched layers, and we use a fluid to drive those. Turns out hydraulic fluid liquid is a little bit better than air for reasons I'll talk about in a moment. We critically, in fabricating these, in this, sorry, I skipped a step here. This, let me use a pointer. This step, we pre-compress the textile. It's called ruching in textile processing or fashion, such that the thing can extend up until some large limit in that direction. Under loading, the elastic channels provide an elastic force that then can be relieved when pressure is supplied. So under this low pressure condition, the elastic channels are resisting the descent of this load, but then when we apply positive pressure, the thing extends in isometric conditions. At low pressure, we produce a larger force. It's shown up here, and then at higher pressure, actually volume is a better figure of merit here. We produce a smaller force like that. And real easy to make. So if you're interested in these, check out our paper, because we have a simple video that shows you how to make them yourselves. The materials are very commonplace and inexpensive. We happen to have a computerized embroidery sewing machine, but I've produced these myself on a conventional sewing machine. There are a couple of tricks to getting the channels routed in these things in parallel. We show in the paper that these things operate over many, many cycles, like thousands of cycles, about as much testing as we do in a research setting. Have some hysteresis, but not too terribly bad. And actually, the energetic losses in liquid operation as compared to pneumatic operation are lower. Moreover, for some reason, I think pneumatics have gained a lot of attention. Soft robotics came out of labs, including chemistry labs, that routinely have compressed air. but it happens that if you inflate something with compressible fluid, you're storing a lot of energy in that fluid. I used to teach a soft robotics course, and one of the least pleasant aspects of the course is that students are hand fabricating these soft robots. They inevitably, a number of them will fail, and so having something explode at 20, 30 psi is a very unpleasant experience for everybody. If you're using liquid, pressure drops almost instantaneously, and so you just get dripping out of the device. So if you're teaching a soft robotics course, using liquid and just a syringe pump or something like that, just manually operated, works well. More recently, we had spent quite a bit of time looking at potential applications of these things, and one area in which analogous devices are already used is in compression therapy. So compression therapies are used for a few different purposes, but some of the most medically significant are as therapeutics for things like deep vein thrombosis or lymphedema that impair circulation in the peripheral circulatory or lymphatic systems. They're quite prevalent, and so so the standard therapy that is intermittent pneumatic compression, which involves sort of garments that kind of squeeze intermittently. You'll see them in just about any hospital these days. So the idea was to adapt these textiles to do this, and rather than simply squeezing, to use a programmed pattern of actuation that might better promote fluid flow. So aiding circulation from the limbs to the heart and so on. And there are analogs of this sort of thing in biology, like in our digestive tract. These are pretty low profile devices. So one need in compression therapies in medicine is for pediatric cases. So existing intermittent compression devices are very difficult to adapt to apply to babies or small children. And so I think one advantage of our approach is our textiles are much lower profile and easier to scale in size. The physical forces are exerted by contractions. We do compression via contraction. So the pressure we produce is based on the hoop stress. So we have an axial stress in the channel producing this hoop stress that's squeezing the limb. And that depends on the T-act. It depends on the radius of the compressed body, the stress in the channel, and other factor that I'm blanking on at the moment. You can see you see experimental characterization here. So this is for a single channel wrapped around a tube over a broad range. We can control over a broad range. We can control variations in pressure quite a bit above some level where we sort of are no longer applying forces to the thing, so it goes slack around the object. So our prototype, I'll show you in a moment, uses 8 channels device. So it's an 8-channel device, which is that's a lot of motors to have around. We also developed a simpler 2-motor version. Both of them involve simple pistons filled with water, driven by RC servo motors. And in this 2-piston version, we use a quadrature driving system to drive 8 channels in peristaltic motion out of just 2 driven channels. So this whole thing can be made pretty small. In some cases, therapeutic devices need to be portable, and this might be a good way to do that. So with that introduction, I'll show some videos. It's not really going to play very well, but you'll see, I'll show you some quantitative data. This is the prototype. So we'd arrived at this design by exploring different configurations. So we actually designed this system to be modular. It's a bunch of independent channels that can be arranged in different ways. This is a sleeve that can be tensioned around the limb and driven to squeeze the limb in peristaltic motion. We can do this periodically, so at very high frequencies. This is volume and pressure. So this is sort of the enclosed areas, the hysteretic loss. So we get higher losses at higher frequencies, lower frequencies, much lower losses. Could drive this up to rather high frequencies if you'd like. Of course, performance becomes impaired as you do so, but multiple hertz, tens of hertz are possible. So this is we captured the shape of this thing using just motion capture markers applied to the device as it surrounded a kind of elastic cylinder. And so from this, you can see sort of how we produce peristaltic motion by controlling the phase offset between adjacent channels to produce a wave-like motion that can promote fluid flow. Oh, there's a better image of this. So these are the channels in sequence. That's their position. This is time. And so you see this sort of wave-like behavior moving along the limb, which you'll see if you want to see a video of that at a frame rate where you can actually perceive it. Grab me later. What it would look like. This is the sort of quadrature kind of two versions. We use 2 ports on each pump and control the phase between them such that we get sort of quarter phase offset between each quarter period offset between each output. So how does this produce flow rate? Well, the theory of peristaltic flow is somewhat classic. The average flow rate, Q bar there, depends on the tube radius, the wave amplitude, and the wave speed for peristaltic motion. Expression's a little bit more helpful when you break out wave speed into frequency and amplitude with parameters that then reference the spatial interval, the distance between channels, and the time shift or phase offset between the channels. You get an expression like this. So the flow rate increases with other parameters fixed, increases with either the wavelength or the frequency. So you need sort of at least a wavelength within the range of the thing. So lambda can be maximized within that range. And then F is free, but there's some trade-offs in different frequencies. A and B are the tube radius and wave amplitude. And results look sort of like this. So as wavelength increases up to some critical value around here, where the wavelength exceeds the length of the thing, we get this sort of linear relationship between wavelength and flow rate. You can see that for a lower frequency peristaltic wave, a higher frequency peristaltic wave, so higher frequency, more flow. And so on. Oh, maybe I had I'll show you. So these data were captured from a model of the limb. So we have a supporting bone-like structure, fluid channel adjacent to that, and an enclosing tissue, sort of a minimal model of the limb that's needed there. We published so I really like this wearable space of soft engineered systems. I think soft robotics within the engineering domain is sort of design, and different design requirements some design requirements may naturally suggest the use of soft materials. In the wearable space, they seem to be quite favorable due to the properties of the body. But we enumerate a lot of examples from the literature and talk about a lot of design considerations involved in animating textiles, so turning them into robotic entities. Among them, key figures of merit are things like, this is one of the figures from the paper, are the elastic parameters of the materials, which is different from the surface hardness. And even within the domain of softness, one has to, which is kind of a bulk or volumetric property, one has to distinguish between the intrinsic softness of the material. So many fiber materials, the fibers are actually quite hard, but their arrangement in, say, a felt might render them relatively soft. Surface hardness, very important for controlling wear in materials. So it's possible, for example, to have very soft materials that are highly elastic, in other words, but are hard, meaning their surfaces resist wear. And all I wanted to talk about here, a lot of this work was the soft textile work. It's work by Mengte Zhu, who is now a research scientist at Meta, working on, I don't know, some kind of wearable haptic stuff. I don't know too much about because I get glimpses. And the gripper was work by Yufei Hao when he was an exchange graduate student in my lab. Thank you so much.